We already talked a little bit about what a polynomial function is, but I'll just really quickly talk about that again. It's a polynomial function that takes this form that you see here. P of x equals, and it's just the a represents a number, the x is a variable, the n is an exponent. So it has those components. It doesn't have things like, down here, 5 to the power of x, right? We said that one's not a polynomial function. It has to have that form, like the first one, x to the power of 5 plus 3, or something similar. So we'll just skip to here. We want to start talking about, what do polynomial functions have in common? And one of the things we talked about, or you looked at, was the end behavior. So when we look at these polynomial functions, we have x squared, negative x squared minus x plus 6, negative x squared minus 8x minus 7. Those are all quadratic. And then the ones at the bottom are all quartic. X to the power of 4, negative x to the power of 4. And then this long one, x to the power of 4 minus 4x cubed, and so on. And it doesn't really matter what these equations are. What matters is they're quadratic and quartic, which means they have something in common when you think of their degree. And that is that they are even degree polynomial functions. So the degree of the ones along the top is 2, they're quadratic. The degree on the bottom is 4, they're quartic, but they're all even. And so they should all have something in common. And then we're going to divide them up looking at the ones that have a positive leading coefficient versus a negative lead coefficient, because those have differences from each other. So starting looking at the ones that have a positive leading coefficient, which are, let's see, this one, that has a positive leading coefficient. So all that means is that the number in front of the x is a positive number. And actually here, all the x's have either a 1 or a negative 1 in front of them. So these are the positive functions. And what do you notice about their end behavior? So what that means is, what happens where the graph extends? What directions do they extend? What we notice is that for all of those ones that are circled in red, the graph extends up into quadrant 2 and up into quadrant 1. Anytime that you have an even degree polynomial function with a positive leading coefficient, the graph will extend up into quadrant 2 and up into quadrant 1. You can see that they have different shapes. The quadratics are all parabolas, and you know lots about that, but the quartics have different shapes. This one almost, at first glance, looks parabolic, although it's not. You can see it's kind of a different shape, more like a U shape. And then this one has kind of multiple maximums and minimums happening there. But the common feature is that they all extend up. And so then if we look at the other ones with the negative leading coefficient, it's the opposite, right? They extend down into quadrant 2 and quadrant 1. So that's down into quadrant 3 and quadrant 4, not 1 and 2 that I originally said. But all those ones that are circled in blue have a negative lead coefficient, and they extend down into quadrant 3 and down into quadrant 4. And that's going to happen, again, for any even degree polynomial with a negative lead coefficient. You'll find they all do the same thing. You should also notice that these all have the same domain. X is any real number, because they extend forever to the left and right. But the range depends on the maximum or minimum value of the function. Because they all actually have a maximum or minimum. They extend up forever or down forever, but not both. The domain is all real numbers. You can put that as XER if you want. X is an element of the set of real numbers. The range depends on the maximum or minimum value of the function. So it could be y is greater than 0. So everything 0 and above. Or it could be y is greater than 4. or it could be y is less than something, depending on which direction it's opening. And if you think about it, if it's negative, it's opening down, so your range is always going to be y is less than, right, less than some value. But if it's positive, it'll be y is greater than some value, depending on what that lowest value is. This next set of functions are all odd degree. We have linear, which are a degree of 1, cubic, which are a degree of 3, and then quintic, a degree of 5. And so 1, 3, and 5 are all odd numbers. These are odd degree polynomials. And we can see some similarities between these as well. All of these ones extend up forever and down forever. So we'll figure out which ones, which with a negative and positive, but let's just talk about the domain and range for a minute. The domain's the same as it was for the even degree, but what's the range for these ones? Does the range depend on anything about the function, or do they all have the same range? They all have the same range. The domain and range of both of these are all real numbers. And another notation, x is an element of the set of real numbers, y is an element of the set of real numbers. Which is good, that's what we have on the chart here as well. Now the positive leading coefficients, I'll circle those in red again. It's this one, this one, this one, this one. Those four are positive lead coefficients because the x has a positive 1 in front of them. So all of those four, they're extending up into quadrant, which quadrant is this? 1. Up into quadrant 1 and down into quadrant 3. That's what they all have in common. The graph extends up into quadrant 1 and down into quadrant 3. And then for the negative lead coefficients, which would be the other four, you see the graph going up into quadrant 2, down into quadrant 4. So there's the note for that as well. Oh, here we go. This last one is talking about zeros, roots, and x-intercepts. Do you know what those things are? Have you heard those words before? Yeah? They're all sort of the same thing. Zeros, roots, and x-intercepts. We tend to use those three different terms interchangeably. They're not exactly the same thing, but they all, for any function, work out to the same numbers. So that's why we interchange them. The zeros of a function are the values that make the polynomial function equal to 0. So if we take this polynomial function, p of x equals x squared minus 4x minus 5, and make p of x equal to 0, then we can solve for the zeros of the function. And that's easy enough to do, factor, or graph, or use the quadratic formula, but I'm just going to factor this one. It looks like I factored it right. X squared plus x minus 5x, which makes negative 4x, and then negative 5. So then the solutions of the zeros would be x equals 5 and x equals negative 1. Those are the zeros of the polynomial function p of x equals x squared minus 4x minus 5. The next column here is the roots. So this is, we're talking about zeros here. we're talking about roots over here, and then way over here we're going to talk about x-intercepts. But like I said, they're all kind of the same thing. They're a little bit different, but we do tend to use those three terms interchangeably. So the zeros, those were the values that made the polynomial function equal to 0. When you're talking roots, it's the solutions to an equation. So you can see this one is not a polynomial function, right? It's a polynomial equation. So there's no y equals or p of x or f of x equals. But it's the same. We're going to solve it the same way. Factor x minus 5, x plus 1 equals 0. And then the solutions are x equals 5, x equals negative 1. Same thing. So that's why we can interchange them. Even though one we're solving an equation and one we are finding the solutions to a polynomial function, it still ends up with the same thing. And then the last one, the x-intercepts, well, those are the points where the graph crosses the x-axis. So you can see there that they're at negative 1 and 5. So they're all kind of the same thing. If you're asked for zeros, if you're asked for roots, if you're asked for x-intercepts, it's all sort of the same thing. We're going to do an activity a little bit later where you're exploring the x-intercepts of some polynomial functions so that you can figure out how many zeros or roots or x-intercepts does each type of function have.